Okay, so today we're going to wrap up section 2.4 over mathematical induction. And this is a method of proving an infinite number of things by only proving two things are true. Maybe we'll go down to the bottom of the page here where we actually have it written out. So if we have a propositional function S with a domain of discourse, which is the positive integers, C plus, if we know that S1 is true, and if Sn is true, then S of n plus 1 is true, then the propositional function is true for all n. And we worked through a few examples of this last time, where we had different
Professor,
kinds.
that's not in the notes I have for chapter 2.4.
Yes.
Which one is this?
This is page 1.
Oh. Sorry, I thought we were starting where we left off.
Oh, I was just reviewing this before we did the next example.
Okay, sorry.
Yeah, that's fine. Okay, so last time we used this principle of induction to prove that this formula works. For example, if we add up the first n positive numbers, 1, 2, 3, all the way up to n, then it follows this formula no matter what numbers you're adding up. So this was our propositional function. This equation was our propositional function in this particular problem. Let's see. And then after that, we talked a little bit about factorials. And this is where we multiply all the numbers counting down from a positive integer. Or for 0, we just have the number 1. And we proved that this inequality was true no matter what positive number we plug in. So let's go to the theorem that we're going to prove today from this section. And I will just organize my notes here, since they seem to have gotten quite a bit out of order. Okay, here we go. So this theorem is something that we saw way back in section 1, chapter 1, and it has to do with counting the elements in a set. So remember these symbols that look like an absolute value, when you write them around the set, tells you how many members are in the set, or how many things are in the set. And here's the theorem. Let X be a set if the cardinality of X is equal to n, so cardinality was the other word for this, then the cardinality of the power set of X is equal to 2 to the n for all n greater than or equal to 0. And I should also remind you what the power set is, since it's been a while since we had to use that idea, at least in the lecture. I think you might have had a homework problem or two that include this idea. So remember, the power set of a set X and we use this notation P of X is the set of all subsets of X. Okay, so basically in this problem, we're trying to count the number of subsets of another set that we're calling X. And for this proof, since we're trying to prove that our formula works for any number greater than or equal to 0, we're going to need to use mathematical induction because it has to work an infinite number of times for any number. So let's start setting up our proof by writing what we're doing and then get started on the base case. So first of all, we tell the reader that we're going to use induction. And then the way that I like to organize my induction proofs is by writing out the two steps. Excuse me, spam call. Writing out the two steps. The basis step and something you might notice about this particular problem is that we're not starting at 1. The smallest value of n is actually going to be 0 in this case. But this actually doesn't make any difference for induction, whether we're starting at 0, 1 like normal, or any other integer. As long as we can start with the base case, whatever it is, and then prove the inductive step, that's showing that the next one is true. It doesn't really matter where we started. So we're just going to start at n equals 0. It doesn't matter. But we might want to make a little note of that. For this proof, the basis case, or the basis step, corresponds to the case where n is equal to 0. So let's figure out what that means. So if we're assuming that n is equal to 0, that means that we're assuming the cardinality of x is 0. What does that mean about our set? If the number of elements in our set is 0, what does that mean?
Does it mean it's an empty set?
Right. So in this case, x is actually just equal to the empty set. So what is the power set of the empty set? Anyone remember? What are the subsets of the empty set? Does it have any subsets?
No.
But you have to be a little careful because the empty set is always a subset of any set, including the empty set. So every element in the empty set is in the empty set because, well, there's nothing there to check. So this is always true. So the power set of our set has one element. Does that match up with our formula? So we're saying it should.
Yes.
Yes, it does match up. So we're saying our power set has
n equals 0. What do you think that'll make the 2?
2 to the 0 power is 1. if that's what you're asking.
Yep.
Okay. So now that we've calculated the number of elements, we should just make a note that this matches up with our formula. So maybe I'll just say this agrees with the claimed formula since 2 to the 0 equals 1s. Okay. Any questions over the base case? Or the basis step?
Don't you need to put the square at the end of the period?
Good question. This was just the first half of our proof, since it's the basis step of our induction. So before we can say that we're finished, we need to do the inductive step, or the inductive case. So this is where we assume that the formula works for n, and we try to show that it works for n plus 1. Let's just write that down. So we assume that if we have n elements in our set, then the number of elements in the power set is equal to 2 to the n, and then we need to show that if we have a set with n plus 1 elements, I'm going to use a different name for it. I'll call it y. Then its power set has 2 to the n plus 1 elements. Okay, so how can we possibly do this? This one is a little bit more challenging, I think, than the ones that we've done so far, and is probably a little bit harder than any of the ones that you're going to do in your homework. So I think I'll probably just show you how to do it. The idea behind what I'm about to do is that we have to relate our new set y with n plus 1 elements back to a set with fewer elements, with n. So what I'm going to do is pick an element from my set and take it out. So let's pick an element. I'm going to call it A. And then I'm going to take that out of my set to get a new one. So Z is going to be the set Y minus A, or the set containing A. And this is what I wanted, because the number of elements in Z is equal to N. And by assumption, that means that its power set has 2 to the n elements. Okay, so how does this help? I'm going to make a little table here, or a couple columns, that lets us compare subsets of Z with subsets of Y. But for the subsets of Y, I only care about the ones that contain A, where A is an element. And you'll see why in just a second. So if you think of the smallest set of Y containing A, well, that's just the set containing the single element A. If I want to get the smallest subset of Z, I can throw that element out to get the empty set. And then we can think of larger elements, or larger subsets of Y, excuse me, maybe a set with A and another element B. I can throw A out again to get the subset B of Z. Maybe Y has more than two elements. Maybe there's a C inside of it. Then I can throw A out again and get a different subset of Z with just the element C. And you can see how you might do this for any subset of Y containing A. So maybe this subset has A and then maybe 4 or 5 other elements. We can again just throw it out, throw A out to get a new subset of Z. So you can see that there's this correspondence between subsets of Y containing A and the subsets of Z. So I'm going to make a note over here to the side that there's a one-to-one correspondence between these two columns. So the important thing for us is that the number of things in this column, the number of elements in this column, matches the number of elements in the second column. But we actually know the number of elements in this column, the subsets of Z. Remember, this is the power set of Z, and there's 2 to the n elements on this side. So what we've done here is we've made 2 columns, and if we match the 2 columns together, we'll get all of the subsets of our set Y. So we have all of the sets containing A in this column, and all of the subsets not containing A in the second column, put them together to get all the possible subsets. And this gives us a way to count the total number. Okay. So I'm going to need to flip to the back of the page. Are there any questions before I turn the page over?
What is our ultimate goal? I know we're doing a proof. We're calculating the amount of subsets for an infinite number of.
Okay, yeah, so I think there are two questions. Our immediate goal is to count the number of subsets of Y, but our bigger goal is to prove this theorem that this formula works no matter the number of elements in our set.
I was just making sure I was on track.
Yeah, it's easy to get lost in a big proof like this. Any other questions? No? Okay, so let's flip over the page and finish off this proof. And let me write down a little bit of what we know. So we know that the power set of Z has half of the subsets of Y, or the power set of Y. And remember from before, we know that the number of subsets in the power set of Z is 2 to the n. And putting these two ideas together, we can count the total number of subsets of Y. So here we have the power set of Y, and we know that the power set of Z is half of the total. So that means 2 times the number of subsets of Z will give us the answer. And then just plug that in, the 2 to the n. And then we can just finish by remembering that when we have two exponentials with the same base, we add the exponents, and 2 is really just 2 to the 1. Then this is equal to 2 to the n plus 1. Now we can say we're done. We counted the number of elements in the power set of Y. And this finishes off the inductive step. So any questions over this proof of the theorem?
Professor,
Yes, go ahead.
so it means that it's just basically if one of the elements will be the subset of the set Z, so it will be contain half of this element will be on the subset Z and the half will be not. That's what you mean, right?
If I understood you correctly, then yes, that's what I mean. I mean, half of the subsets of Y contain A, and half of the subsets don't contain A. And that's why it broke down into these 2 columns.
Okay, yeah.
Mhm.
I got it.
Can I see the last little bit that you just
Oh,
wrote?
sure. Or is this what you meant?
Yeah, that's what I meant.
Okay. Any other questions?
Thank you.
Let's see. So it is 4:45. Okay, so since we do have 30 minutes, I think we need to maybe try to get started with the next section.